Welcome to the deep dive. Today we're really opening up the vault and exploring the actual architecture of secrecy itself.
We're getting into some heavy stuff. Douglas Stinson's Cryptography Theory and Practice, which is, a core academic text.
And we're using it to understand not just how encryption works, but what makes a system genuinely secure.
Exactly. I mean, we use this stuff every single day. Every time you buy something online, send an email. But what does secure actually mean mathematically?
That's our mission today. We're going to track that definition from ancient codes that were trivial to break all the way up to the algorithms that protect our digital lives now.
So let's start at the very beginning, the classic setup.
You have Alice. She
Huh.
wants to send a message, the plaintext, to Bob.
But the channel is insecure. There's always an Oscar, the opponent, listening in.
Right. And a crypto system is just the rule book for this whole game. It defines the plaintexts, the ciphertexts, the keys, and the rules for encrypting and decrypting.
And you can have all those 5 things perfectly defined, and the whole system can still be, well, completely useless.
Which brings us to the Caesar cipher, or the shift cipher.
The poster child for instant failure.
So it's really simple arithmetic, right? You just take a letter, say A, and shift it forward by a key, K. If K is 3, A becomes D.
B becomes E. You just wrap around at the end of the alphabet. The math is fine. The problem is the key space.
There are only 26 possible keys.
That's it. So Oscar, our opponent, he doesn't need to be a genius. He doesn't need a supercomputer.
He just has to try K equals 1, K equals 2, K equals 3.
Exactly. He just turns the dial until the garbage turns into English. We call that an exhaustive key search.
And the book gives that classic example. Oscar gets some ciphertext, he tries K equals 9, and suddenly it reads, a stitch in time saves 9.
And boom, game over. He has the plaintext and the key. It's not just weak. It's, trivially cryptanalyzed.
Okay, so that failure leads to the next logical thought. If 26 keys is way too few, let's just make the key space enormous.
And that's where the substitution cipher comes in.
This is where things get really interesting because it seems like it should work.
It does. Instead of a simple shift, you create a totally random mapping. A goes to Q, B goes to X, whatever you want.
And the number of possible mappings, the key space, is 26 factorial.
Which is, it's a mind-bogglingly huge number. It's up 4 thousands with 26 zeros after it. You could not brute force that today. Not even close.
So wait, if an exhaustive key search is completely impossible, why isn't this the perfect cipher? What's the attack?
The attack isn't on the lock. It's on what's inside the lock. It's the language, English.
You mean because it's predictable?
Deeply predictable. A substitution cipher is monoalphabetic. One letter always maps to the same other letter. And our language leaves statistical fingerprints all over the place.
Okay, tell us about these fingerprints.
Well, think about letter frequency. In any normal English text, the letter E shows up about 12% of the time.
So Oscar just counts the letters in the ciphertext.
He does. And whichever one appears most often is almost certainly the encrypted E.
And once he has E, he can look for common pairs, the diagrams like TH or he.
Or the trigrams, yeah. The most common one is the HE. Once he's pretty sure which ciphertext letter stands for E, he looks for a common 3-letter pattern that ends in it. That's probably the HE.
So the enormous key space, the 10 to the 26 possibilities, it's irrelevant.
Completely. The redundancy of the language just undermines the entire system. It's broken by simple frequency analysis.
So the next step had to be about hiding those frequencies, which brings us to the Vigenère cipher.
Which was called chiffre indéchiffrable for, centuries. The unbreakable cipher.
Because it's polyalphabetic. It uses more than one alphabet for encryption.
Right. You pick a keyword, let's say deep. It's 4 letters long. So you encrypt the first letter of your message with a D shift, the second with an E shift, the third with an E shift, the fourth with a P shift.
And then you cycle back to D.
You cycle back. So a plaintext E might get encrypted with a D shift one time and a P shift another. It completely smears the frequencies. A simple letter count tells you nothing.
That seems like a huge step up. So how is it finally broken?
With a brilliant piece of analysis from 1854 called the Kościuszki test.
Okay, how does that work? How do you find a hidden keyword?
It's a surprisingly simple idea. If you see a short repeated sequence of letters in the ciphertext, say XYZ appears twice, it's very likely that it's the same plaintext fragment encrypted by the same part of the keyword both times.
Ah, so the distance between those two XYZs must be a multiple of the keyword's length.
Exactly. So if you find repeats that are, say, 15 letters apart and others that are 20 letters apart, you look for a common divisor.
Which would be 5. So the keyword is probably 5 letters long.
That's your best guess. And once you think the keyword length is, say, 5, you can break the ciphertext into 5 separate piles.
Where the first pile is all the letters encrypted by the first letter of the key, the second pile by the second, and so on.
And what you're left with is 5 separate messages, each one encrypted with a simple shift cipher. You're back to cracking Caesar.
Incredible.
Yeah.
So before we move on, the big lesson from classical ciphers seems to be that the size of the key is almost a distraction.
It is. The real vulnerability was the data itself. Human language is just too full of patterns.
And that realization is what pushed cryptography into the modern era, into information theory.
Absolutely. Thanks to Claude Shannon, writing in 1949, he's the one who gave us the mathematical language to even talk about what security really is.
And he broke it down into 3 pillars, right? The first is computational security.
That's where we live today, mostly. It just means breaking the cipher would take an absurd amount of time and money. Billions of years on the fastest computers. It's feasible, just not practical.
Then you have provable security.
Where you mathematically prove that breaking your system is at least as hard as solving some famous, really hard math problem like factoring huge numbers.
But the holy grail, the theoretical ideal, is unconditional security.
Unconditional, meaning Oscar could have infinite computing power all the time in the universe, and he still couldn't break it, period.
And this leads directly to Shannon's idea of perfect secrecy.
Right. And all that means is that seeing the ciphertext gives you 0 new information about the plaintext. The encrypted message tells you literally nothing.
For that to happen, Shannon proved that the amount of key material you have has to be at least as big as the message itself.
And every key has to be used with equal probability, which leads us to the one and only perfect cipher we know of.
The one-time pad.
Invented over 100 years ago. It is truly mathematically unbreakable.
Yeah. Why don't we use it for everything? There has to be a catch.
Oh, there's a huge catch. It's key management. The key has to be perfectly random. It has to be the same length as the message. And this is the killer. You can only use it once.
If you reuse a key, the security just vanishes.
Instantly. And you can imagine trying to securely share a unique, gigantic random key for every single email or credit card transaction. It's just impossible.
So in the real world, we're stuck with computationally secure systems. And we're still haunted by that old problem, the redundancy of our data.
We are. Shannon formalized this with a concept called entropy, which is a measure of uncertainty. The flip side of that is redundancy. The source says English has a redundancy of about 0.75.
So 3/4 of a typical English sentence is basically predictable.
It is. Our brains fill in the gaps. And cryptanalysts exploit that with a concept called the unicity distance.
Which is, what, the amount of ciphertext you need before the key becomes obvious?
Exactly. It's the point where all the wrong keys start producing gibberish, and only one key produces something that looks like English.
This is a huge point. Even with the massive key space, if the unicity distance is small, you're still vulnerable.
It's the whole story. Remember that substitution cipher with its 10 to the 26 keys? Its unicity distance is about 25 letters.
Wait, only 25. So after 25 characters, there's likely only one key that works.
Statistically, yes. That giant key space becomes completely irrelevant because the language itself gives the game away.
So to build a truly secure computational system, you have to find a way to just destroy the statistical structure of the language.
You have to obliterate it. And that's the whole idea behind modern block ciphers. They're what we call product ciphers.
They combine simple operations, substitution, and permutation over and over again in many rounds.
Right. They're often built as substitution permutation networks, or SPNs. You have S-bosses that substitute bits to create confusion, and P-layers that shuffle the bits around to create diffusion. The goal is to make the relationship between the key and the ciphertext incredibly complex.
But this new complexity meant the attackers needed new tools.
They did. And the 2 most powerful tools ever developed against these kinds of ciphers are linear cryptanalysis and differential cryptanalysis.
Okay, let's start with linear. What's the core idea?
It's all about finding a statistical shortcut. The analyst looks for a simple linear equation that connects some plaintext bits, some ciphertext bits, and some key bits.
It's not looking for a perfect connection, though, right?
Not at all. It's looking for a bias. A relationship that holds true maybe 51% of the time instead of the random 50%. It's a tiny statistical impurity.
But if you have enough data, thousands of plaintext ciphertext pairs, you can use that tiny bias to start guessing bits of the key.
That's the attack. It's a statistical sledgehammer.
Then there's differential cryptanalysis. That one's different.
It's conceptually beautiful. It doesn't look at one message. It looks at the difference between 2 messages.
How does that work?
The analyst takes 2 plaintexts that have a very specific tiny difference. Maybe just one bit is flip. They encrypt both, then look at the difference in the resulting ciphertexts.
And they're looking for a predictable pattern in how that difference ripples through the algorithm.
Exactly. They're looking for a differential trail. If a certain input difference leads to a certain output difference more often than random chance would suggest, the S-boxes are leaking information, and you can work backwards to find the key.
Which brings us perfectly to the case study of DES, the data encryption standard.
Adopted in 1977, it was a 16-round iterated cipher.
And the controversy from day one was its key size, right? Only 56 bits.
Yep. Even back then, people were saying that 256 was on the edge of being brute forceable, and they were right.
By 1998, a machine was built, the DES cracker, that could find a key in less than a day. So it failed from key exhaustion, just as predicted.
It did. But that's not the really shocking part of the story. The real shock came later, when researchers like Byam and Shamir published their work on differential cryptanalysis.
What did they find?
They analyzed the S-boxes in DES, those core substitution components, and they discovered that they seemed to be specifically, almost perfectly, designed to resist differential cryptanalysis.
Hold on, differential cryptanalysis was made public in the early 1990s. DES was designed in the mid-1970s.
That's the stunning part. It strongly implies that the designers, probably the NSA or IBM, knew about this incredibly sophisticated attack vector decades before the public did.
They were building defenses against attacks that nobody else even knew existed.
It shows you how deep the race between the lockmakers and the lockpickers really goes.
And that race is what led us away from DES and toward its replacement, AES, the Advanced Encryption Standard, in 2001.
Right. AES is another iterated block cipher, but it's much stronger, with key sizes of 128 bits or more, and it's built to resist all the attacks we currently know about.
So to bring it all together for the listener, we've seen classical ciphers fail because language is predictable. We've seen early modern ciphers fail because key spaces were just too small for Moore's law.
And what we have today is security based on computational complexity. AES isn't secure because it's provably unbreakable like the one-time pad. It doesn't have perfect secrecy.
It's secure because the amount of data and the sheer computing power you would need to run an attack like linear or differential cryptanalysis is just, it's infeasible.
It's beyond the practical reach of any adversary today. We rely on it being too hard, not impossible.
It's an amazing journey. From a simple code that 26 tries will crack, to a system where you need an impossible amount of resources to find just a tiny statistical bias.
It's an endless creative contest. And that brings us to a final provocative thought for you to chew on. If the designers of DES were secretly building defenses against attacks decades before they were public, what completely new, unseen vulnerabilities are already known to the people designing the systems that will one day replace AES?